Okay, we can go ahead and start on Zoom. You can hear me well, right? Before we proceed, uh, sure that it's well heard. Okay, thank you, Aiden. Let's see here. Um, not sure. This is not sure. Okay, perfect. This is good. Just wanted to show you. Okay, we can go ahead and start. Good afternoon, guys. Happy Wednesday. So, a few course logistics to speak about is obviously the announcement of yesterday, and that was regarding the final exam. We discussed in class last lecture whether you guys prefer to have it before Thanksgiving and either after Thanksgiving. So, a few students did not really care to have it either before or after. So, they are down or open to either option. And then we decided to do a vote. And so I announced a vote yesterday. And from looking at the stats from it, everyone prefers to take it before Thanksgiving break. So then you would leave after Thanksgiving break and have nothing else left. So the quiz will be closing tonight. So we'll give everyone a chance to to take the quiz by tonight, the survey quiz, and then I'll make an announcement about the actual date, the finalized date. And that's going to be based on, obviously, on the vote, the higher vote that the students chose. In terms of the style of the final exam, it's going to be similar to the midterm. It's going to be take home. You'll have like a whole day to take it, and it's going to be similar style of questions to the homeworks and to the actual midterm. So that is that. And so that is regarding the final exam. I'll post an announcement sometime tomorrow to announce about that. In terms of assignments to be done, their assignment two is to be due this Sunday, so just be aware of that. And I'm planning to post the third assignment, which is the last assignment, roughly about chapter five, sometime this week as well, so that you have all the assignments out. So assignment three will be the last assignment that we have, and then our final exam plus the current assignment that is out. So I'll post an announcement to explain everything again, and then just make sure that the deadlines are known ahead and early so that everyone has a chance to prep. And I'm hoping that this flexibility with the final can kind of give you a break since some students like to travel early or leave early. Um, okay, so that is all I have for the course logistics. Do we have any questions before we begin on Zoom or on here? Okay. Let's talk a little bit about the modules where we are. So today we're starting a new chapter, and that is going to be chapter 5. And it's still related to the network layer, but we are talking about the control plane, not the data plane. So we need to know to understand and differentiate between them both. That is before we start. And then we'll dive into the control plane and several algorithms. We'll speak about one algorithm today, and I mentioned a few videos for it. So just a recap quickly of last lecture and what we spoke about. We talked about generalized forwarding, which is the emerged modern technique now being used when it comes to networking. And we have explained that there's usually traditional way of routing or forwarding, and that is going to be installed within these physical devices that we have. But over time, we have managed to find a programmable way to have a hub control or a centralized control that can take control of everything, making the decisions plus the data forwarding, which is usually the same per device. So we kind of removed the brain of the routers and the devices themselves, and we made it being controlled by the software-defined server or that specific their role when it comes to that specific technique. So we talked about access control lists, and basically all you need to know about them, they are being used by routers, by firewalls, by IDSs, by IPSs as well, to filter traffic and accept traffic, meaning that they can accept, deny specific traffic, and they can also, meaning when they accept, they know where to forward it. In terms of forwarding, we know we have specific algorithms and we have specific filters or specific details from the datagrams that we are receiving to look for. So the idea is that when we use it for network traffic to allow incoming traffic, is we want to examine the packets that are coming in to see if they match the specific rules we have embedded into these devices, then we allow these packets to come in. So that is the idea. The filtering criteria can be done through several ways. We can do it by the transport layer. We can do it by the network layer, source IP, destination IP, TCP, or UDP. So that is how usually typically firewalls work. So when you get a ring of firewalls, any systematical devices, when it comes to the network, whether they're virtualized or whether they're physical, they are using this specific technique. And now this technique with the access control list is also being used by software-defined networking. And here's a figure that we said a rule comes in, and we have a variation, a packet comes in, sorry, and we have a variations of rules that get tested. If a match is found with the packet details that goes hand to hand with the rule, then we accept the incoming packets. If there's no rule, then it goes to discarded. If there's no match, then it also goes to discarded. So if we want to accept actual benign incoming packets, then we must have rules to match those packets as well. So we have to keep in mind that not only we want to deny the malicious packets or the packets that are not needed for our internal network, but we also need to keep in mind that the packets that are coming to the internal network, we do have rules that are set up for that. And here's two examples that we gave on how to do the access control list. So we talked about last chapter, we wrapped up the network layer from a data plane version. And so we talked about what's inside a router. We talked about the IP protocol. We talked about generalized forwarding, software defined, which uses a match and action technique. And it's basically the same match and action technique that we have with the access control list. We talked about OpenFlow, which is the protocol P4 that is being used by software defined networking. So basically with the match and action abstraction that we have is that there's a table, there's going to be embedded within every router, and it's going to have those rules. If there's a match, then an action gets taken. For example, we have here a forward action, we have a drop action, we have a send to controller action, meaning that we're not sure what to do with it, so we send it back to the controller for further help. And the details that we can specify within the rules is like destination IP address, source IP address, and we can do various things such as a specific protocol within the transport layer like UDP or TCP traffic, the network layer as well. Even the link layer if we want to filter for the packets based on their MAC address. So these are another examples that we have destination-based forwarding, firewall, we have layer 2 forwarding. And we know that the match and action is being used by several of these kind of functions like a router, switch, NATs, and firewalls. And we know that what each of these are responsible for. This is basically showing you the OpenFlow match and action again scenario on a visualization way with the routers. And we moved on to middle boxes. And middle boxes, anything that is installed between the router and the other devices that we have, internal, external network. And there's going to be variations that we have, like we said, web proxies, load balancers, web caches, firewalls, IDSs, NATs as well. That is going to be middle boxes, anything that is going to be installed within the sender and receiver to do some sort of service for us, whether it's a network address translation or firewall to block or filter for specific traffic. These are identified under or as middle boxes. We took a look at the IP and the hourglass and how everything revolves around the IP and where are the current middle boxes fall with this specific hourglass modernly now. We talked a little bit about the architecture of networks, and we know that what is defined and what has been agreed upon in terms of standards by IEEE is that the intelligence goes to the end systems. So the end systems handle the intelligence, data reliability, data control, data flow, and that the end-to-end is that is what networks follow, is that the network itself just tries to forward packets or retransmits packets, and it doesn't handle the intelligence. So it is kind of like a lightweight sort of technique or model that we have. And that is it. So that is what we talked about. And the last thing is we talked about is fragmentation and reassembly, is that when a specific transmission link within the infrastructure that we have, and here we have a figure that has many links that is installed, and that is obviously to deliver or to send and receive specific packets, is that we have an MTU, which is the maximum transfer size that we can send. And if we have a size that, if we have a packet that is a higher size than the allowed link size, then we must fragment it and reassemble it at the host. And we talked about how do we reassemble and how we fragment it in this specific technique. And that is it that we wrapped up last chapter 4. So now we move on to chapter 5, and we're going to talk about the network layer from a control plane perspective. So let us dive into that. Okay, so as usual, the slides some of the slides are borrowed from the book, and they can be accessed there, and the class is recorded, and you can access the recordings on the Zoom section of WebCourse. Make sure this is sharing. Okay, good. So when we talk about the network layer, we know that the network layer and network, when we talk about the all-side model, and you get asked, what is the network layer main functions? And we know the main functions of the network layer is going to be obviously to send packets, meaning that to forward the packets and route those packets between a host and another host. So for example, between maybe UCF and a student that is accessing or sending specific packets or working with that specific server within UCF. So basically host to host. The transport layer kind of does a little bit of a different where it transfers the data from one processes to another, meaning that if you have a pool of users and all of these users are using the internet in various ways live, we can allow each user to request specific data, and that data is going to be received to them. And we know how to do that when we discuss the transport layer. So now we're moving from the control plane to we're moving from the data plane of the network layer to the control plane. So we want to understand the principles behind control decisions. How are they made in the network? How does the network make a decision on how to forward the packets that we have? And how do we decide where packets go and how routes are being chosen? So we're going to study 3 components that we have. So we're going to study the traditional routing algorithm that is found in an early generation of networks, kind of like peer-to-peer or link state, and this is vector routing. We'll talk about SDN controllers, which we already have talked about, but here more kind of in depth. And then we'll talk about network management and configuration. We'll also cover concepts, those concepts and how they're implemented in the real world life or real world systems. And then that includes specific models that are being used now, such as OSPF, BGP for routing. We have OpenFlow, ODL, ONS that are part of software-defined networking, and they fall under that. We'll talk about the ICMP protocol, how it handles messages and error messages across the network layer. And we'll talk about other things like SNMP or Yang or NetConf, which are mechanisms that are going to be used to monitor and configure network services that we have. So here's the roadmap that we have for chapter 5 and the control plane chapter, part of the network layer, is that obviously we're going to do an introduction. And basically is the introduction is going to be about the control plane. And the control planes is that we have many paths within the network infrastructure and we have routing tables. So how do we manage to route these specific packets? We'll talk about routing protocols that we have. And we'll study two major types, which is link state, where the router knows the full map of the other routes or the other paths that we have. And then we have distance vector, where routers will share information only with our neighbors. So these kind of routing protocols are going to be the main logic that we have behind dynamic routing decisions. We'll talk about OSPF, and this is focused inside an autonomous system like an ISP. And this uses shortest path first. And we will come to all of these, obviously. We have routing among ISPs. This is how the ISPs communicate with each other. So we use PGP, and that is policy-based routing. And it has political side and business rules that affect the route selection with it as well. So that is how ISPs kind of communicate with each other. And then we'll talk about software-defined networking more, and how the router, how the controller makes all the decisions that we have. And we talked about one example of that is using OpenFlow. And then we'll talk about the ICMP message, like the ping and trace routes. And we'll talk about network management lastly. So beyond routing, how do we monitor and configure and control those devices? So here's what you need to do. The network layer has two main functions, and we have said that over and over, is that we have the data plane, which is forwarding packets from one router input to appropriate router output. And then we have the control plane that is determine the route taken by packets from source to destination. And so that is going to be kind of like one is going to be forwarding and one is going to be in process of kind of like the big brains to make the logical decisions or the movements for those packets. And there's going to be two approaches that we have, or two main model designs for how control is going to be organized. So the first one that we have is the traditional per router. That means each router runs kind of its own routing algorithm, and decisions are going to be distributed and made locally. The other way that we have is software-defined networking, whereas we have a central controller that is computing all the routes for all the routers. That is kind of easier, gives us an easier way of management and global network visibility. So these are the network models or designs that we have, and how it evolved from the per router control, which is the traditional, to now what is modernly used, which is the software-defined networking. Now let's understand the per router control plane. This is the traditional way of how each router would have its own routing algorithm. Okay, so let's focus on this specific design first. So we have many routers here, and there's paths between the routers, as we see. And then obviously we have incoming packets that we must deal with, which is something that is typical. So the control plane here in the network layer would try to find the best path. The data plane would just be responsible of forwarding those, basically implementing what the control plane tells it to. So, and we know that each specific router has a local forwarding table. And this is basically that maps the header values to the correct output ports that we have. So when a datagram arrives, and we will see here, so for each router, we have like a cylinder kind of. And basically that means each router is responsible for its own control logic. So there's not like a one place controller that is managing all of those. And then we have these local forwarding table that's kind of like stored within these routers that are gonna have a header and an output to the header. And we're basically gonna do matching, which we have discussed, and specifically prefix matching with the longest prefix matching as well. So each router is gonna have packet that comes in, it's gonna have a header, and it's gonna determine based on the header, if it matches, then it's gonna direct it to the specific output. So you can see here at the bottom that we have in this specific router, when a packet comes in, we have to match the header that is coming from the packet, and it's gonna determine to us which route we should take, which will be here, kind of route 2 or path 2, okay? The routing algorithm that we have is going to be how we can exchange communication with other routers. So this is the process that allows routers to learn about the overall network structure. And we'll talk about different algorithms that we have. So the red lines just want to here that I want to display is that the algorithm that we are using is going to communicate with the other routers to find the most efficient and shortest path that we have. And then we can see the routers kind of working together. So we know that each one is running its own algorithm. Each one has its own local table. And even though that the routing is going to be local, each one has its own decision. And then finally, I want to highlight the control plane and the data plane within this. And so the control plane is going to be obviously the big brains when it comes to the routing, and the data plane is just going to forward the data or forward the packets that we do have. So this separation kind of give us a way of organization such that it makes the internet more scalable, flexible, and kind of resilient. Any questions so far? Okay, good. So now we'll talk about software-defined networking, the most modern way now. And we do have it's under the acronym of SDN. And now the control plane is going to be moved out of the routers and going to be in a centralized remote controller. And this controller is going to be responsible for the forwarding for the forwarding of each router. So here, as usual, we have the same path, the same figure from the last slide. We have incoming packets that are coming in, and we have multiple routers here. So we need to know how we can route those as well. So here we'll have a remote controller. This can be a server that we have, and this server has an overall view of the entire network and can commute the paths for the data flow. So by having this kind of centralized way or centralized server, we can have a better management and have faster updates across the whole network. Each local table for each router is going to be stored within the remote controller. So rather than the local router is making its own decisions, the server or the controller is going to make the decisions for the routers. And we see that here, the controller would communicate with each router and it would monitor the network and send continuous updates. And here we have the CAs, which is the control agent that will communicate directly with the router to receive, to communicate with the router and the server to receive the latest forwarding table that we have. And finally, this is the same separation that we have in the last slide, that the control plane has been just changed here with having a remote controller rather than the data plane is still the same like how we had in the traditional way of networking. So now we move to routing protocols. We have link state and we have distance vector. So we'll focus on those specific protocols next. So here, this is a general figure that we had, and we had over and over as we discussed many chapters, whether it was the transport layer or the network layer. And this is here just trying to show you that we have variations of topologies of networks, whether it's a mobile network. Here we have national global ISPs, enterprise networks, is that we have different a diversity of kind of networks, and they need to all be staying connected. So all to stay connected all depends on the network layer, the routing algorithms, right? So the goal of when we talk about routing algorithms is that we want to have the good paths for the packets, And these are going to be the paths that are sending hosts to receive hosts through network of routers. So we have those routers that are communicating with each other, and we need to make sure that we find the best path. Obviously, there is going to be details for the paths or some drawbacks for each path that we do take. Each router is going to have like an exchange process or a participation process, either forwards the packets or reroutes based on the algorithm it has. So the first thing that we must do is we define a path. And the path is going to be basically a sequence of routers that we have to take a place that the packet goes through and reaches a specific host, a specific node. And it's going to be an initial sequence that starts and it will end at the final destination for that packet to be sent. And then each specific hub, like for example here, we have the red line that is kind of, let's say, one of those laptops or hosts are trying to reach this specific server. Each initial sequence of every router is having some sort of decisions to get there. Okay. We'll also study what makes a good path. So that is the drawbacks that we said with taking paths. And there's several things that can kind of have an impact on the path. Like we have cost, we have the fastest, we have the least congested. This is something typical, like when you're traveling, maybe to get to campus on your car, you have multiple paths, and there's multiple costs with each path. Whether this one is longer, more congested, you would have to pay tolls. So that is typical as well with the network. And with all these factors that we have and trying to balance all these factors, routing is like a top 10 challenge in networking. So it combines optimization, decision making, and real-time adaptation as well. So kind of talk about a little bit about graph theory or network science here. We can have a graph abstraction, and we can look at the graph in a way that we have nodes and edges, and the nodes are obviously going to be the routers, and the edges are going to be the links between those routers. And then for each link that we have or each edge, obviously it's going to be a weighted link, meaning that we have a specific weight that is added to that link. It could be a time, it could be cost, it could be various things. Here it's not really defined specifically, but it's going to be link cost. So we represent the network as a graph, graph G, where we have N's and E's. So N's is going to be the nodes that we have. So the nodes we have is here is going to be U, V, X, Y, W, Z. These are different routers that we have. And the links that we have are going to be the edges. So this is the set of links that will have connections between them. So those are going to be our routers, the N, which is a set of routers. And we have a set of links. So the set of links is going to be obviously which routers are connected. So when we say that we have a set of links such as UV, then that means there's a direct link from UV. You might realize here, we do not have a set link between U and Z. So that is not to be found here as well. So there's going to be routers that don't have links with each other. That's why we are going to take other paths, and we need to be smart about taking those paths. Here to talk about a little bit about the cost definition is that we know that each edge that is there associated has a cost, and that is usually written as C sub A comma B that we have here. C here, and that's pronounced as C sub AB that we have. So that is the cost of the direct link. So the cost of the direct link from U to V is going to be 2 here that we have. And so those costs are obviously going to be set by the network operator and can represent different things, like we said. It can be a fixed value like 1 for all the links, whether we have a connection or not, ones or zeros. It can be the inverse of bandwidth. It could be the inverse of congestion. If the link is heavily congested, then it cost us increase. So the main idea is that the link, the weighted link between each router is going to tell us some sort of intrinsic detail about the router, whether it's expensive, difficult, congested, or it could be just a connection that has been made between those routers. So this routing algorithm classification kind of chart is going to help us, and we're going to ask ourselves two questions. So the horizontal is going to ask, do we have any global or decentralized information? And the vertical here is going to ask, how fast do routers change, meaning adaptation or kind of diffusion that happens. So the axis that we have here is going to help us map where each routing algorithm fits best based on how it operates. So we're going to talk about the algorithms in a general review, and then we'll dive into one of the algorithms. So the first one that we have is global routers, global routing information. So in global routing, all the routers within the graph that we have or within the network kind of know the complete topology and the link costs. So every router has like a full map of the network and computes its resource independently. So for example, here we could have 4 students and they are walking from here maybe to the library. We each one of you guys know the universal path of what route that you're going to take, whether you go through classroom building or the finance building or whatever building, so that you have an understanding of which routes each user is going to take. So those are going to be link state algorithms and like OSPF. OSPF, we're going to break it down in detail, but this is kind of giving you a general way. And we have decentralized routing algorithm. These are going to start with only local information. So meaning that each router just knows its neighbor and their link cost. So that maybe its neighbor, if we have 2 students here, they can only know information about themselves. They don't have an idea or a full overview of the whole topology or structure of the network. And the key they change updates using distance vector algorithms, and that is going to be used in RIP, which is an algorithm that we have. And then obviously we have static and dynamic algorithms. So static routing is going to just assume the network changes very slowly, and the routers manually configure, and they rarely get updated. So that works kind of best for like predictable networks. And we have dynamic, which adapts automatically or kind of to the topology or the cost changes. So that kind of updates on a time base or in kind of response to events where it needs to have an update. So that kind of adds flexibility to extra control plane processing. So these are the most 2 important categories that we have, is that all the routing algorithms are going to either fall under a link state algorithm, where it's global and dynamic, or a distance vector algorithm where it's decentralized and could be also dynamic. So those are the foundations of routing protocols that we do have. Okay, so we so far have talked about the introduction. We differentiated between a control plane and a data plane. We talked about the traditional versus the modern way of kind of routing. We talked about link state and distance vector. So now we'll focus on the link state, and that is used by modern routing. They operate using obviously global information. So these are the other things that we have to also cover, but we might not get a chance to cover today, or we'll cover them in the next couple of lectures. Okay, so the one algorithm that we're going to talk about is the Dijkstra algorithm. Have you guys heard about this algorithm before? Yes? Okay, good. So some of you might have heard of it in where data structures, CS2. Discrete math, data structures, maybe data algorithms. So we're going to explain it here, and I have also put videos up that explain this in like kind of more in a simplified way, or another point of view that you can check out as well. So the Dijkstra algorithm is kind of assumes there's a centralized view of the network, and every router knows the entire network topologies and all the link costs. So it's kind of a global algorithm. And this is achieved through a link state broadcast. So routers flood information about their neighbors and link cost. And then at a result, we have every node that has the same information about the network graph. This is why link state uses global knowledge. So um, the first thing that we do is compute least cost path. So the idea is that we're gonna always trying to find the shortest path, the least costly path for us to take, for starting from the source node or starting from the main or first router. And the algorithm builds kind of like a forwarding table, and this table kind of tells that we keep track of, that tells us um, the next hops that we have and their cost. And then we always take the shortest cost, and it gets repeated. So it's a iterative process that we have, meaning that after k iterations, the router knows the least cost path to k destinations that we have, and that depends on the amount of nodes that we have or the amount of routers. So let's talk a little bit about the notation of the algorithm that we have, and where we have to describe a little bit about the algorithm, we have C sub XY, and this is the direct link cost from X to Y. So if X or Y are neighbors, then C sub XY is going to be in infinity. So if there's a link between each node to our nodes that we have, there's going to be an associated cost. We're going to put an infinity if there is no direct link between them. DOV represents the estimate of the least cost path from the source to node V. PV is going to be there's going to be the previous node that we have along the path from the source to V, and this is going to be explained more with the examples that we have. And we have N prime. This is the set of nodes that we have whose least cost path are already defined or already are known for us. So the first thing that we do is the algorithm begins with the initialization phase. So here we're trying to compute the least cost path from the source node. So the here we have in line 2, n prime is going to equal it's only going to contain u. So n prime equals open bracket that we have, and we have u. So this means that u is the only node where the shortest path is definitely known at the start. This is the starting node that we have, okay? And then from line 3 to 6 is going to be for every v in the network. So if v is going to be adjacent to u, then we set d of v equals c sub uv. So that means we're going to assign the direct link cost from u to v. Otherwise, if they're not neighbors, then we set d of v equals going to be infinity. So basically, if there's a link, associated cost is going to be with it. If not, then it's going to be infinity. And then we kind of go through a loop process, an iterative loop phase. So now we enter the main loop from line 8 to 15 that we have here. And this process is going to continue until all nodes are going to be included in the n prime, or part of that routing, the routers that we have or the nodes that we have. So after, and this is kind of like the updates part of the algorithm that we have, is that after each iteration, we find the node, which is W, that is not yet n prime, and that is going to be the maximum DW that we have, which is the smallest current path. And then we add W to n prime, locking its shortest path. And then we update DV for all neighbors, V of W that are not yet finalized. So this is going to make more sense with the examples that we have. So this process is going to repeat it one node at a time, and we grow the set of the shortest paths from the source, okay? Here's a little bit of an analogy to tell you about the Dijkstra algorithm. from a human analogy, or kind of like finding the best route in a city. So you kind of have a city map where the intersections are going to be the nodes, and the roads are going to be the links that gets you from one intersection to another, and that we each specific kind of road or intersection or link is going to have a travel cost, whether it's time, distance. Here we have it as time. So you start from the main point, which is going to be the U point, that is known as the start node, and we want to find the shortest route to every other location. So at first, you only know the roads directly connected to your home. So the rest are going to be kind of unknown. And as you travel, you discover newer nodes, and then you know that they are shorter than your original path, then you take those newer nodes. So it's just like kind of exploring a city step by step. For example, if you move to Orlando and then you are working, you have a specific path that you're taking from your house to your work. And then maybe one day there was going to be kind of construction, so you might take another route, and or you explore other routes and you find those are the shortest route, or kind of the route that is less congested, depending on obviously what is making sense to that user. But here, obviously, every cost is going to be depending on what we assign it to for each link. Okay. So continuing on the analogy that we have is home intersection is going to be the source node U. Travel time on the road is going to be the link cost CA/B. Closest interaction visited, that's going to be added to the N or N prime. That confirms the shortest path. And then we discover shorter roads, and then we update DV values such that all interactions are mapped out, and then all the shortest paths are known. So each time you visit the closest interaction, you lock in the shortest route, and it adds it to N, and then you update the estimated travel time, just like the Dijkstra. How do you guys pronounce it? Dijkstra. Dijkstra. So the J is not pronounced. Okay.
Professor pronounced it Dijkstra. Dijkstra.
Dijkstra. Okay, thank you. Because the J I always pronounce it. So Dijkstra, yeah, that is much easier. So the process is going to continue till every node has the shortest map. So kind of like you can think of Dijkstra algorithm as a GPS that always expands outward to the nearest xword route until the map is fully optimized. Oh, I skipped myself. So let's look at a few examples. Now we know how the Dijkstra algorithm works kind of theoretically. Let's apply some examples to get a sense of how it works. So we obviously have on a graph abstraction or router abstraction that we have multiple routers, and there's going to be 6 that are here. And we'll count them very quick. We have UV, XY, and WZ. So they're going to be the same ones that we have here. These are going to be the iteration steps that we take to find the shortest paths. And obviously we start at N prime, which is going to be node or router U. So that is the first thing that we must define. Also, we know that there's going to be link cost between every link between the nodes. And we have the specific formula here for the Dijkstra algorithm that we have discussed in the previous slide. So the first thing that we do is obviously we're going to start at node U, and then we're going to see all the connected links that are connected to node U. So here we compare node U with V. So does node U and V have a connection? The link cost is going to be 2, so we're going to write it here. I have transitions for every step, so just bear with me here. And then we're going to look at U to W. It has a direct connection. And note that we're only focusing on the direct connections. We don't need sub connections or sub paths that are connected. So only direct connections are going to be counted. So W here is going to be the associated link cost is going to be 5. W to X, U to X is going to be 1. This is our associated weight. And U to Y and U to Z, which we have here, U to Y and U to Z, is going to be infinity because we don't have a direct link that is connecting those. So the first thing is that we write all the link costs. Then from looking at the table, we can say, hey, what is the shortest link cost that is associated? And we take that path. So then we take the path. We see the smallest one, and it's obviously going to be U and X. And as you can see here, there is a coordinated shortest path between U and X. So then we add X to the n prime, and then we continue the next step. And you can see here that step is going to be taken here. Okay, so we do the same from when we get to X. Once we get to X, we have to keep in mind that we're carrying a 1. So we recalculate all the other paths that we have. So we kind of update all the link paths at each iteration that we have. So once we get to X, there's one thing to note. You can now go back to the previous node. So U to V is impossible to go to, and V is not included up top because it is the start node that we have. So we look at X to V. X to V in the last iteration is 2. From X to V in this second iteration that we have is going to be 1 plus the 2, that is 3. So we're going to leave the lowest cost that we have. So we leave that as 2. We take a look at X and W. And X and W here is not, or was originally 5. And from this specific phase to get to W, we have the link cost that we're carrying plus 3 is going to be 4. So we update the W here from 5 to 4. X is going to go, there's nothing going to be here because there's not going to be a self loop that we have. And in the initial phase for Y and Z, they were infinity. So let's take a look if there's a connection. From X, yes, we can get to Y. So the link cost is going to be 2. So that is going to be 2 here. And Z still does not have, we don't have a direct connection to it. So that is going to drop as infinity. So let's see if that is right. So yes. And then we repeat the process. Then we take the shortest path again. So from X, the shortest path that we do have is that this specific path is going to be 3, which is kind of more for us. From X to W is 4, and to Y it's 2. So we must go to Y next, okay? Here's one thing I want to note. D is going to be the cost. P here is going to be the where the link is coming from. So now we know that U and V has a connection now, and it is going to be from U. So now we know the shortest path for this X is going to be Y, so we add Y to the next step, and then you can see the connection here. Does that make sense so far, guys?
It's only 2 because we're not going from U from X to B because then will be 3, right?
Yeah, because the original phase that we had, U to V is short, but from the second iteration step that we have, it is longer. So at each step, we must recalculate. So do not use the old numbers that are in the table. So you must know that you are updating the table, the numbers every time. So we do the same thing. I'm going to do it one more time so that everyone understands, and then we will move on from this slide. So we're at Y. So then we recalculate everything again. Note that we're basically trying to add all the other nodes that we have. So we must add node Y, which is already here. So what do we have remaining? We have node V, node W, and node Z to include. Once we include all of them, then we can move on. Okay, so we're at node Y, and the W here was usually 4. And we are carrying here 2, and there's 1 here. So the path is going to be from Y to W is going to be 3. So this needs to be updated. Okay. From Y to V, there's no direct link. So we're going to keep that same number. Y to X is going to go as nothing because that it has been already visited. Y to Y, there's no self loop. So there's going to be nothing. Now we have a direct link from Y to Z, but we must remember that we are carrying 2 here plus 2, so that's going to be 4. So that is going to be updated from infinity to 4. So let's see if that's right. correct? So now we want to take the shortest algorithm, the shortest path that we have. So the shortest path, obviously, for us is going to be V, but we cannot get from Y to V directly. So we may take this specific path that we have. So note that with this algorithm, the Dijkstra algorithm, it does not really care if you go to the initial phase, as long as you are finding the shortest path, as usual. And this is kind of computing the other steps that we have. Yep, and then we have visited all the nodes, so then we have the full the full overview of the shortest maps between each router. Okay, once we have the full map from node U to all the other nodes to the shortest possible route that we have arrows that determine which are the final chosen paths. And what we can do is we can have a kind of a forwarding table. And this kind of forwarding table is if we want to get to destination V, the shortest path to it is going to be UV. And all the other nodes such as X, Y, W, and X, the shortest or the startest node is going to be UX. That is going to lead to all of them. So remember that it's only thinking kind of the start node to the next phase, and then we must repeat the process. That's why the ongoing link is always going to be UX for all these other nodes. But once this gets to X, obviously that path is changed based on the path that we have here. So it's going to be XY or YW or YZ, okay? So that is just trying to highlight that. So the forwarding table is going to be the practical output to the Dijkstra algorithm, and it's going to translate the shortest path into the actual routing decision that we have. So every router builds a similar table that allows data to move through the network along the lowest cost paths. We have any questions? No? Here's just another example that we have. It's going to be basically the same thing, but we just have a little bit of a different figure that we have. And the same idea is repeating here. U is our starting node. We have other nodes. We must find the shortest path. So the first thing that we do is we note annotate all the link costs that we have. So that is going to be the link cost. We're going to see what is the lowest link cost that we have, which is going to be U to W, which is going to be here, which is 3. So we take that shortest path. And then once we get to 3, we do the re-update. Then we take the next shortest path. This is going to be a U to X. And then that process gets repeated again and again till we find till we have a map, a global overview of the shortest paths for each specific route. Okay. This is just trying to show you. Yeah, this is trying to tell you that we can trace the subnodes that we have, and ties can exist. They can be broken arbitrarily. So that is just to note that we have. But it's basically the same thing that we have. Now to talk a little bit about discussion about the algorithm, because every algorithm or every model has some its limitations that comes with it, is that we want to look at two things. We want to look at the algorithm from complexity, algorithm as a complexity, and the message as a complexity. So let's talk a little bit about the algorithm. And we suppose that the network has n routers or n nodes. For every iteration that we have is that the algorithm must check all the other nodes that are not yet in the set of n to find the one with the smallest path as we have been doing. So that means roughly n iterations, and then each one involves up to n comparisons that we have. So that gives us a complexity about O of n to the power of 2. So it's the complexity problem that we do have. So these are going to be obviously, there's going to be efficient versions that we have that kind of calms the network down, like a priority queue or mini heap that can reduce this complexity of the algorithm. So the algorithm is very simple, but it can get expensive as the network grows more large. The message complexity, meaning that we have each router and they must broadcast a message or communicate with the other routers, meaning that links to information must be shared across the network. So the broadcast messages also is going to be about a ON problem. So the complexity of it becomes the same as the algorithm complexity. So I just want to highlight here that the Dijkstra algorithm works best for small networks, but as networks scale up, both computational work and message exchanges can grow very quickly. And I have a human analogy to understand this more. We know that there's two types of work that are happening in the Dijkstra algorithm. One is computational work for the algorithm, and one is messaging, meaning communication. So here we have is a router must think, obviously, before making a decision. So it checks the possible routes that it has before making a decision. Obviously, the decision is going to be based on the shortest path. More routers, more thinking. So this goes roughly like to the power of 2, meaning if you double the routers, the work grows 4 times. For the communication, is the same thing, is that each router must communicate with the other routers that we have to share the link information. So it becomes an n to the power of 2 or a complex problem. Here's another analogy that I spoke about with the teacher, and this is more in detail about the discussion based, is that the algorithm complexity that we have is we have a teacher, for example, and I'm trying to find the shortest path for each student from the dorms to the classroom. So I have to compare obviously all the possible paths for every student that is coming to class. So the more students that I have, is going to be the more comparisons she has to make or he has to make. So with 5 students or with a low number of nodes, that is completely fine. But as that increases, it's going to be a kind of a very or a huge impact to calculate that. So that's the ON part of the problem. The complexity is the same thing, meaning that imagine the students are sharing information with each other about which paths they taken and the shortest paths for them. They have to talk to each other. So with many routers talking to each other or many students talking to each other, this can become a confusion or it can become very complex problem. So more talking, that's where the message is exchange parts. Here we want to look at the most allocations possible. And this is relation to the traffic load of the Dijkstra algorithm that we have. So here we're going to have routers, D routers, D, C, B, and A, or you can say A, B, C, and D, to however you like. And obviously each link cost is going to increase with the traffic, and that's shown as 1 plus E or plus E. And everything looks stable at first, but let's see what happens when the routers are doing the recalculation based on the new traffic volumes. So here we have, as traffic increases, certain links are going to have a huge cost. And that is, for example, 1 plus E or the 2 plus E. So the routers are going to recompute the shortest path using the new values. And now because the links have become more expensive, the traffic shift is going to shift to the other side. So this causes the network, or this causes change to the data route. So kind of like link swap. So then we swap to the other side that we have, kind of like flipping. And once the traffic moves to the new side, it becomes more congested as well because it has cost or congestion that comes with it. And then the router is going to be coming kind of oscillation kind of in behavior, like it's swinging back and forth, meaning it's flipping back and forth to try to find the most available path. So that is kind of like this scenario is trying to demonstrate that, because that we know that one feature of the Dijkstra algorithm is it reacts and reacts to the cost changes and kind of changes or adapts its ways. So we have modern protocols that has like stabilizing mechanisms like hold down timers, like kind of similar to what we had for packet retransmission or packet lost. We have route damping, we have smoothly functions to prevent rapid changes. So that is needed. We needed to add these stabilities to make sure that the route, this specific algorithm doesn't have the oscillation problem. Here's a human analogy that kind of just demonstrates the same idea we discussed in the previous slide, is that we have maybe three routers, D, C, and E, or you can say three delivery drivers, and they all need to deliver the packet to the same destination, which is A. And we have two main rows to get to A, let's say left and right side. So each driver obviously is going to want to choose the fastest route. And the initial situation is that each driver sees that the left side is open, it's not congested. This is the same way that the router thinks. So all of them take it. And as all three uses the same road, traffic builds up, so it slows it down. So routes exchange to the right side. So they all switch it over to the other side, meaning the right side becomes more congested. They kind of have like a back and forth behavior, and there's no coordination. Everyone just reacts to what has a faster throughput or a faster path. So that results in a constant oscillation. So there's no steady flow of traffic. So the next thing that we're going to talk about, which is going to be our next lecture, is going to be distance vector. Talked about link state, and we're going to talk about distance vectors. And once we know the link states and distance vectors, all the other algorithms are going to be fall under these specific protocols. So that makes total sense. So that is all we have for this lecture. Next week we're gonna reminder that next week I made an announcement that the lecture is not going to be in person, and this is the first lecture that we had that is not in person. So it's going to be recorded and uploaded, but it's basically going to pick up on top of this. I'll post an announcement tomorrow regarding the final exam time, based on the vote of the results. And I'm gonna post the assignment sometime this week as well, so that you have everything out, so you can try to plan or schedule your schedule to the way that you like. Okay, so if there's no questions, you guys are dismissed, and I'll see you on Monday.